Morning, everybody.
Good morning.
Morning.
Maybe. Questions about anything before we get going?
Can I give you a warning, Dr. Joe?
Sure.
So they're working on my internet right now, so it may go in and out. So I may kick out. So just a heads up.
Yeah, I appreciate that. My obviously my internet has not been the best, especially the last few days. I actually contacted Sprint. I actually contacted Sprint about it the other day or yesterday, and they're supposed to be sending me a magic box that's supposed to help with the internet connectivity. So we'll see what happens.
Nice.
Yeah, I have no idea what the magic box is supposed to do, but we'll see what happens. All right, first thing I want to do is write down a homework assignment I would like you to do for next week. That first problem is out of chapter 2, but I wanted you to do the same kind of stuff that we did in section 8.1, which talked about does a certain distribution fit the data that you have. So it was that goodness of fit tests idea. I've also already typed all of the data in associated with these problems, and you can find it on Moodle. It should be uploaded to Moodle, and it should say Chapter 8 homework. It's an Excel file at the top, so should be able to find it relatively easily, but let me know if there are any issues with it. But I figured if I make a typo and hand it out to everybody, then everybody has the same typo, and I can still grade the same work. But if individual people make typos, then I've got to grade several different versions of typos. So I went ahead and typed it all in. But I do ask that if for some reason you do see a typo, don't correct it because I want to be able to grade everybody else's stuff. I went through and checked it. I'm fairly confident there aren't any typos, but I'm not going to make any guarantees. That was weird. All right. Any questions about anything before we get going? Doing the same stuff we did last time with the Wilcoxon sign test. All right. Well, let's do this problem then I've got up on the screen here. Like I said, I wanted to do basically today. I just want to do more examples out of section 5 from chapter 8, since we only had the chance really to do the one test or the one example last time, and then there's a couple of other types of examples that pop up in this section. So I want to make sure that you all had an example of each thing. So in this particular one, they've got weights of grape flavored Jolly Ranchers, and we want to test whether or not the median is greater than 5,900. So for part A, they ask us just to use the sign test. Pardon me. So when we do the sign test, we just count how many are actually above the median and see if that is a rare event relative to the median actually being 59 or 5.9 in this case. So for part A here, we need to count of the elements that are in this range, how many of them are greater than the 5.9. And so it says 17 out of the 25. And if we wanted to know whether or not the 17 out of the 25 is actually a rare event or not, we would use the binomial distribution. Actually, I need to know, before I do that, I need to do 1 minus that.
What the count if command? What was that one? It was like count if.
Oh, I'll go back. Let me go ahead and go back to it. Here it is. So it was the count if. I just highlighted the range of data. And then I have to put, remember, I have to put the greater than or the less than sign inside the quotes to let it know that, to convert it from a text thing over to a logical operator, if you will. And then the ampersand just says I'm going back to the numbers. Is that what you needed to see, Michael?
Yes, thank you. I appreciate it.
Yeah, you're welcome. All right. And so this one now, I'm going to calculate a p-value associated with that 17. So I want to know what's the probability that we get 17 or more values above the median, assuming that the median is the 5.9. So I'm going to use I do 1 minus because I need to do above 17. So I'll subtract off the 16 or less from 1. So I'll use 16 for the number. There were 25 trials. Since we're dealing with the median in this case, the probability of success for any given trial is 0.5. And we do want cumulative here. So the p-value associated with this would be 0.054. So if we were using an alpha with 0.05, we would not reject.
Dr. Joe, why did you do 16 trials?
Because remember, I'm doing the complement. I need the probability that we had 17 or more. So I'm doing 1 minus 16 or less. Or 16 or fewer, I should say. Making sure my grammar is proper because I'm always so worried about such things. So if you were looking for your so this was your p-value associated with that particular statistic. If you were interested in what your critical region should be, you would need to calculate, well, if you check that, if I do 1 minus, that was weird. 1 minus, if I do 17 in this case, for 25 trials at probability of 0.5 and true. Notice that I get a probability of 0.02 in that case, so that my critical region would be, I would need the number of successes, which I think your book typically refers to as y, to be greater than or equal to 18, which we didn't have. So that was, again, we did not reject. In both cases, we do not reject the H naught.
So, Dr. Joe, could you just explain, like, why looking at the 0.02, why you know it had to be 18 again?
So that one is really more of a trial and error kind of thing. I know it's not.
Oh, that's right.
Yeah, I know it's not 17 because 17 was at 0.05. So honestly, if I personally were looking for that critical region, I would probably do several values here. And then do 1 minus the binomial distribution for each of these. Oh, I didn't hit an equal sign. That's why it's not popping up. I would do 1 minus the binomial distribution for each of these. And then copy down. And so here was, this is the first spot where I get below 0.05. So then I know that I did this was 1 minus 17, so that would tell me it was 18.
Oh, okay.
It's more, honestly, you would, before we had things like our calculators and computers to do this quickly, they have these different tables made up, and there's a few in the back of the book where you would just go down your table and figure out where it would be. In your book, there's a cumulative binomial distribution table. somewhere. If I can find it real quick. Yeah, it starts on page 575, and then you could scan down the table relatively quickly and figure out where that number needed to be.
Okay, thank you.
You're welcome. Somebody is trying to chat with me. Oh, that was Ashlyn. Congratulations, Ashlyn.
Yay, Ashlyn.
Thank you.
Awesome.
That's awesome. That's what, like I said, that's the whole goal of going to this college is to get exactly that. So that's awesome. Congrats. All right. So let's.
Dr. Joe, you said the whole goal of going to college, and then your audio decided to. And it was funny.
Well, at least I wasn't saying something inappropriate at the time, I suppose. No. And I said the whole goal of college is to get it exactly that. To be able to say I accepted a job offer. I got into grad school or whatever. So that's exciting. I'm very excited. All right. So let's talk about Part B. So Part B, we're going to use the Wilcoxon test statistic instead. So to use the Wilcoxon, the first thing we have to do is rank each of these by the median. So the first thing I need to do, actually I'm going to do this first. Let's take each individual piece and subtract it, or subtract the median from it. So I just did that. All I did was the A1 minus the 5.9 because that was the median. And now I'm just going to copy to the same shape here. And I'm going to delete out these last two because there's no data in those two cells. So those are the signs, but remember we have to rank the magnitude of these things. We don't want to rank them with the signs. We want to rank them by magnitude, about how far away they are. So I also need to do, and I could have done this all in one step, by the way, but I also need to do the absolute value of each of these numbers. In other ones, I'll probably do it all in one step rather than two steps here. But just to show you what's going on. So the first thing was I just computed the differences from that each individual data point was from the median, the purported median, and then took the absolute value. All right, so these magnitudes are what we need to rank. But I also want signed ranks. So this I will do at the same time. I need the sign of the difference. Is it positive or is it negative? And then I'm going to multiply that by the rank of the individual data point with regard to the range. And then I need to make the range an absolute cell reference here. All right.
Wait, stay on it for a little bit.
Oh, sure. So you said it right as I hit. Got you. I heard you right as you said. No, it's okay. It was just perfect timing. So again, that SIGN command is just picking off, is it positive or is it negative from this number? And then we're ranking the magnitudes. So that's what the second command is doing.
So do we always need to do the two separate cell ranges?
No, you don't. You could have just done this one. So you could have just done the second one. I could have done the second one by, let me do it off to the side so I don't have something different here. So I could have just done, I have no idea why that came up with a 4. Delete that out of there. I could have done the first one by just doing the absolute value of each data point minus the 5.9. And then move this over. What is that? 9, 3, 4, 5, 6, 7, 8, 9. Copy down. Like that. I could have done just the one. And then here I could do the sine function of, I would still need to do this minus its median. Because I need to know whether or not the difference is positive or negative. And then do the rank command here. Well, if I actually type the word rank, that would be helpful. And then do the rank command here. I could do it that way. Is that what you were asking me? Could I do it in one step? Yep, could I do it in one? And this is what I'll do later on, is I'll do it in one step rather than two. But I was just trying to show kind of the process of what was going on as well. But I can do it this way too. So I can just do it in one step. But I do need a step where I do the differences one way or another. So you'll notice that I'll do the same thing over here and just show you that I get the same numbers. And apparently I'll do it quietly. So if I copy this over and down, and get rid of those, I should get the exact same things over here, even though I did a different command. Which I do. So yeah, you could have done it either way. Except there's one thing I forgot. I've forgotten both of these commands. Remember, we have to rank these in ascending order rather than descending order. So I need a 1 at the end of that. Remember, the idea behind the Wilcoxon statistic is to give more weight to things that are farther away from the purported median. So I need to rank order them in ascending order, and the default for the rank command is in descending order. So I need to change it to ascending. So I need to put a 1 in there. That's actually important. It flips these things around. So get rid of that, and I would do the same thing. I would do the exact same thing over here. I need to make sure I change this to a 1 on the end. Same idea. All right, and then again, notice I just get the only reason why I'm doing it twice is because I'm just showing you get the same thing. The second one's the one I'm going to do more often anyway because it's shorter to only have to do it once instead of twice, like basically what Michael was mentioning. All right, so our test statistic here, the W, the book uses W. So remember, this test statistic here is just taking the sum of all of these values, all of these signed ranks. So just adding up all of those 25 ranks, and we get 171. So then we can calculate, pardon me, you can do it a couple of different ways. Probably just as easy to do it as just like a z-score. You would take your test statistic, you would subtract your mean. The mean in this case is 0. The mean for in this case, what we're doing, the mean is always 0. And then you would divide by your standard deviation. And remember, the standard deviation in this case is the square root of the 25 times the 26 times the 51 over 6. So it's n, which is 25, times n plus 1 times 2n plus 1 divided by 6. So your z-score in this case, so this is your z-score. remember, we're using the normal distribution to approximate.
Dr. Joe, can you go back to the test statistic again?
Sure. That one?
No, the other. The z-score.
The z-score. That one.
What are the numbers again? I've forgotten.
So the B21 is just your test statistic. And remember the mean of the... So I'm just going to type it off to the side. The mean of W is 0. The variance of W is n times n plus 1 times 2n plus 1 over 6. So now go back over there. There's where those numbers are. That help?
Immensely.
Oh, good.
I don't think I actually had the variance written down, so that would make sense as to why I didn't know where that came from.
Yeah, there you go. I don't think I actually wrote it or typed it on whatever day that was. It's just been one long day. I can't differentiate between it's today Wednesday. I just can't differentiate between the days. But it was in the video that I had you watch. All right. Anyway, so there's our z-score.
You definitely just turned into a robot. Just to let you know, so I don't know what you said.
Oh. I don't remember where I stopped. I was complaining about everything running into one long day.
That's fine. We can just leave it there if you want,
okay.
honestly.
All right. So there's our z-score. So we're doing an alpha equal to 0.0. Well, it doesn't even tell us what the alpha is. But if we did an alpha equal to 0.05, our critical value at 0.05 would be 1.645, which is certainly greater. Even if we were at 0.01, we wouldn't reject because I think we need 2.33 for 0.01. But if you wanted to do your p-value now, remember we have to do the p-value a little different. So remember that when you do we talked about this on Monday for certain. When we do the Wilcoxon statistic, either for a particular experiment that we're doing, either the sum that you can possibly get is always going to be odd, or it's always going to be even. Okay, you can't get evens and odds from the same experiment. It's either always going to be an odd number or always going to be an even number. So when you're trying to adjust for your normal distribution for that continuity correction that we've talked about before, instead of doing a half a unit like we did before, we have to do an entire unit. We have to do a whole unit. So if we want to figure out the p-value for this one, we're going to do the normal distribution here on this z-score. But I need, no, not that z-score. Sorry. We need to go, let me write it this way before I start typing in a formula. We need to go the probability that W is greater than or equal to 170 rather than 171 because we have to do that whole unit correction. And if I'm going to go 170 and higher, which I know I'm going higher by the way that the hypothesis test is stated as a right tail test, and by the way that the z-score is a positive number, I know my probability needs to go up from 171. To do the unit correction, I need to make sure I go down a unit to catch 171 on the way up. So when I do this, I would need to do 1 minus the... I'll just do it as normal distribution as opposed to... Whoops, I forgot to hit tab instead of what I hit. All right, so the normal distribution The number that I want is 170 in this case instead of 171. The mean is 0. The standard deviation is that 25 square root of 25 times 26 times 51 over 6. And I still want true here. So we get a p-value of 0.011. I'm calculating p-values just like I would calculate p-value for any other normal distribution problem that we do. I'm just doing that full unit continuity correction. And again, the reason why we use a full unit over a half of a unit is because when you do the W statistic, it goes up by it goes up by 2s rather than by 1s. So you can't get values, you can't get 170 as a value. You can't get 68 as a value for this particular one because I knew I got an odd number.
So if your test statistic was 170, you wouldn't change anything?
I can't get 170 here. If I got 170, I would use 169. What I'm saying is, since I got 171, I know that 170 is not a possibility for this problem.
I see.
The reason why is because for this one, I have an odd number of things in my sample. So the middle number, the middle rank is definitely going to be 13. And again, when I'm saying this, I'm assuming no ties. If there's a tie, then what I'm saying is not right. But we're supposed to have continuous distributions here, so we shouldn't be having ties. Okay, there should be just integer ranks all the way through. So we shouldn't have ties. If you have ties, then this is not, what I'm saying is not true in general. But the reason why I always would get an odd number in this case is because the middle number is odd. And the other things around, if I go symmetric around that odd number, I either get 2 evens or 2 odds. When I add those 2 numbers together, I always get an even. So when I do the sum of all of these things, I get a bunch of evens plus 1 odd. So it has to be odd all the time. If this number were even instead, I would be matching, I would have an equal number of evens and odds for my ranks, so the sum will always be even. So that's how I can tell whether or not it's going to be even or odd as far as my test statistic goes, is if there's an odd number of things in my sample, this test statistic will always be odd. If there's an even number, it will always be even. Again, assuming that I don't have those averages in there. All right. Actually, I'm not sure the averages are throwing off that much, but anyway, right now the whole assumption is that we can't select the same thing twice because we have a continuous distribution. All right, how about part C here? This is a little bit of a review. This one asks for a t-test. So, I hate automatic substitution.
You didn't want the copyright symbol?
No, I did not want the copyright symbol at all. All right. So one of the things that I did not mention last time is that when the development of this particular theory for the Wilcoxon sign rank test is that even though you don't necessarily know what the distribution is to start with, the assumption is that the distribution is symmetric. It's symmetric about its median. So if you have something that's a very, very skewed distribution, this sign test doesn't work for a small sample. It still work for larger numbers because you're still going to be, even if it's skewed, you're still going to be doing samples and you still have things that tend towards a normal distribution at that point. But if it's not symmetric, this isn't a great test to use for tests about the median. But anyway, back to what I was talking about with the t-test. We know that the t-test is a symmetric distribution, and the mean and its median are the same for the because it looks like a normal distribution. It's just a little bit wider. So for a t-test, we would just be doing a t-test for the mean being 5.9. So to do that in this case, I would just take the average of the data, which is about 5.99, and then I would calculate a t-score in this case. So I would take that, oops, I need a parenthesis. I would take that mean and subtract off the, oh, I need a variance too, I bet. Let's do the variance of this. If I'm going to do a t-test, I need both of those statistics, right? I need a mean and a variance. Okay, so now let's do this. I'm going to take my mean and subtract off the 5.9. So that's just our x bar minus mu. Sample mean minus population mean. And then divided by the square root of the variance divided by the sample size, which in this case is 25. So this is our ordinary, usual test statistic when we're doing a t-test.
When you do n minus 1.
That's when you do your degrees of freedom. You still divide by n for your standard deviation estimate, but you do n minus 1 for your degrees of freedom. So this is still your test stat. And then if you wanted to know the p-value, you would do the t-distribution. In this case, I can do a right tail. And the value I want is that 2.6. And like Sam said, I have to do n minus 1. So in this case, it'll be 24. And the p-value is 0.0077-ish. So remember when we did the stuff with the t-distribution, we assumed an underlying population that was normally distributed. When we make the assumption that the underlying distribution is normally distributed, notice that p-value went a little bit less than what the p-value was for the Wilcoxon statistic, which is even better than what we did up here for just a regular old sign test. So the different assumptions here that we're using are giving us different results based on based on just the assumptions that we're making for the individual tests. This one, remember, the sign test usually isn't exceptionally good because we're not taking into account anything with how far something is from the median. This one's taking into account distance from the median, taking into account those magnitudes. But the only assumption we make here about the distribution is that it's symmetric. For C, when we're doing a t-test, we're not only assuming symmetry about its mean and about its median, but we're also assuming that the underlying distribution is a normal one, which is why we would get that nice bell-shaped curve, even if it is a little bit wider, which is why the p-value even went down even further here, because we're making an extra assumption about the underlying distribution. And that's what it was talking about. That's what that last part was asking about, as a short comparison.
So in part C, since our p-value would be less than the 0.05, we know that's not a good assumption to assume that it's underlying normal?
No, you would have to do a goodness of fit type of test if you were trying to see if it was a decent assumption or not. That would be a different test to run.
Okay.
That p-value just says if you know that it's a normal or can safely assume that it's normal, then the median really is not 5.9.
I see.
That p-value being that low is that you're pretty confident that median's wrong. Other questions on this one?
So what do we do for D?
That was what I was just saying. The D part is just the comparison of the three ideas and why they look different. So part A, you're not taking into account any magnitude from the median. Part B, you take into account the magnitude from the median, but only assume that the distribution is symmetric. C, you're assuming that the underlying distribution is normal, which is why the p-value went down even farther. That was what D would be. All right, let's look at the next one, 8.5-5 here. So this one has paired data, and it's asking you to do a Wilcoxon sign test on the paired data, basically looking at if the median GPA in the fall and the spring are, well, either different or it says using your knowledge or experience, if you will, construct an appropriate alternative hypothesis. So when it's paired, and these are paired data, the first thing that we're going to do is subtract to get the pairings here. So I'll subtract the A1 and the B1, and then just copy that down. Now I can do this in this case because the data are paired. If they're not paired, I wouldn't want to try to subtract them because doing a difference across doesn't make any sense. There wasn't any rhyme or reason why they were done that particular way, especially if it was done randomly. But in this case, it's randomly select a student and do 2 observations of the same student from fall to spring. That's why we're doing the difference. That's what it means to be paired. If I did a random selection of students in the fall and then a separate random selection of students in the spring, I would not just subtract across. That wouldn't make any sense. All right. Now, I know it said, based on your past experience, make a hypothesis test, but just looking at the signs of these things, what does it look like the GPA is doing from fall to spring?
It's rising.
It looks like it's going up, right? So probably an appropriate hypothesis test would be that the median is equal to 0, that paired difference is equal to 0 versus is that the median is actually greater than 0. That looks like an appropriate hypothesis test in this case. All right, so again, the first thing we need to do is, these are the values that we need. We need to rank them by magnitude. So I do need the absolute values here. So I'll just do that below. Oops. I would do that below, except I typed it in wrong. Try that again. Let's see. Is that all of them? Yeah. So that's the absolute values. And now we need to do the ranks, but I also need the signed ranks. So I'll do the sign of this value times the rank of that value relative to the whole list. Make that absolute cell reference so that I can copy it down. And then again, unlike the last time where I forgot to do this, make sure that you have ascending order. And then copy down. Your test statistic W now is the sum of those signed ranks. Notice in this case we did get a tie. Your z-score will be that Wilcoxon statistic divided by the square root of, how many are there? 15, so it'll be 15 times 16 times 31 divided by 6. And in this case, we can see that we're not going to reject because we're not above 1.645 here. So we do not reject based on that z-score. And now if you want an approximate p-value, we're still going to adjust by 1. So we'll do 1 minus the normal distribution, 53. Mean is 0. Standard deviation is still that 15 times 16 times 31 over 6. And we want cumulative. So again, the reason why I'm using 53 here is because our statistic was 54. We're using a full unit correction because of the way the rectangles go. The mean of the Wilcoxon statistic is still 0. The variance is still n times n plus 1 times 2n plus 1 over 6. So that's why we have that standard deviation. And I'm doing 1 minus because I need to go to the right tail. We're doing a right-tailed test here. And our p-value we see is about 0.066, which again we would see that we do not reject. Questions on that one? Okay, so this one, I'm not going to go all the way through this example right now just because of time. I'll finish it up on Friday. But this one's a little bit different. Notice that the previous example we had paired data, and we did a subtraction first and then checked whether or not we thought the median was 0. In this case, though, even though they kind of look paired the way that they're listed out, these are not paired data. Notice that the data that we have here are 10 bulbs selected at one manufacturer randomly, and then a different set of 10 bulbs selected at a different manufacturer. Okay, so if I want to talk about something about medians here, about whether or not the median for X and the median for Y are the same, if we're trying to see if the medians are the same, I don't want to try to subtract first because these are not paired. Okay? So in order to be able to do this type of testing, whether or not the median for X is the same as the median for Y, we have to do something a little bit differently. It's going to look similar, but we're going to have a slightly different way to calculate our test statistic, which is also going to change what the distribution of the test statistic looks like as far as the mean and the variance. So just in the interest of time, we'll go through that next time of how we do that. Because like I said, it's a slightly different test, and I don't want to rush through it. I want to make sure it makes sense for what we're doing. So we will go through these last 2 examples next time. All right? Any questions on anything?
Are you
I did. Is it on? Still written on the whiteboard that I had?
Is it?
There it is. So this is, these are the problems that I have assigned for next Wednesday. I've already typed in all of the data in an Excel file that's posted on Moodle. This first one's not in Chapter 8, but I want you to do the goodness of fit test and see if a Poisson distribution is a good fit for that particular distribution. So all I want from 2.6-15 is to take the data set that's there and see if a Poisson distribution is a good fit. So the context doesn't really matter as far as that goes. I just want you to take the data that's in Excel and see if a Poisson distribution is a good fit for that particular set of data. Other questions at all?
Are you doing office hours today?
2:00. Yep. I'll be. If you got questions, just shoot me an email and I'll start a meeting.
Okay, thank you.
Yep. You're welcome. Anything else? Nope. All right, everybody. Have a good one.
For you.